This is our third video with Exponents IB style. So I'll do, looking at number 5, I'm going to do 5, A, and then D, perhaps. Okay. And then let you go practice and then check the answer key. Okay, so they tell you to factor. So I have this 2 to the n plus 3 plus 2 to the n. Well, I can rewrite this as 2 to the n times 2 to the third plus 2 to the n. I can clean this up now. So remember this, working backwards, you'd add them, since the bases are the same, you add your exponents. Since they're adding, you can just give them both the same base and put them together with multiplication. I can go ahead and say, well, I have a 2 to the n in both terms, so I can factor that out. And I can clean this up even farther. I know that 2 to the third is 8, plus 1 more is 9. So you could tell me 2 to the n times 9, or you could tell me 9 times 2 to the n. However you'd like to write that problem is great. But that, it doesn't look like what we're used to saying is factored. I was doing air quotes and you couldn't see them there. There you go. But it is. That's what they're looking for. And then let's look at, notice in C, these are actually both perfect squares. So this is the difference of squares. Try that. I want you to try this one by yourself. This one, excuse me, this is a good case of doing a U substitution. So here's what I notice. I have 3 and I have 9. Well, I know that 9 is the power of 3. So this is 3 squared to the x plus 4 times 3 to the x plus 4. I could say this is 3 to the x squared. So here, now I can let U, not me, equal 3 to the x. And this, hopefully you recognize it pretty quickly that factors. That's U plus 2 squared. And therefore, this factors down to 3 to the x plus 2 squared. Okay, the next set tells us to simplify. Well, I'll do the first one with you and let you go try the other two. On that one, I have 3 to the n plus 6 to the n all over 3 to the n. I'm going to do something similar when it comes to factoring. Well, hang on. This, I know that 6 is 3 times 2. What I recognized is that I had all these, and there's my final step there. I had these 3's, and I wanted to get 6 in terms of 3, so that's why I recognized that 6 is 3 times 2. This would be 3 to the n plus 3 to the n times 2 to the n, all over 3 to the n. Well, now you notice in my numerator here, they both have a term 3 to the n. So I can factor it out. This is 3 to the n times, well, 1 plus 2 to the n. Check and make sure, distribute it back. This is 3 to the n. This is 3 to the n times 2 to the n, all over 3 to the n still. Notice they're going to cancel. And this becomes 1 plus 2 to the n. Okay, I want you to practice these other two. And then let's look at, on number 7, they've given us 3 to the x plus 2 is equal to 1 over 27. And I had somebody in first period want to use logs, and you can, but why? No. What I see is that 27 is the power of 3. And so 1 over 27, well, this becomes, if I want to give them the same base, I can make that exponent negative. Okay, and if the bases are the same, I can set my exponents equal, and therefore x was equal to negative 5. Cool. The next one, I really like 7C. 7 C's. Never mind. Okay, when I see this one, I recognize that 2 and 4 can both be powers of 2. So this is 2 squared to the x. In other words, this is 2 to the x squared plus 2 to the x minus 20 equals 0. Here's a great place to let U, not me, equal 2 to the x. It's still funny to me every time. I'm so sorry. This factors nicely what is it, minus 4 times plus 5. And now what I have is that u either equals 4 or u equals negative 5. And so let's check and see. We have not answered the question because they asked us to solve for x, and we've solved for u. Sorry. Okay, so this is 2 to the x equals 4, and this is 2 to the x equals negative 5. Well, 2 to the x equals 2 squared, therefore x equals 2. This is an answer. But over here, notice they're saying, what can I raise to and get a negative value? Well, if I raise it to something really, really big, it's just going to get to be really, really big and really, really positive. If I raise it to something really, really negative, so let's try this for just a second. If I say 2 to the negative, I don't know, this means 1 over 2 to the, I forgot how many zeros. Okay, but what happens is that this denominator is going to get ridiculously large. And so I have 1 divided by some ridiculously, that has the same number of zeros, just pretend. It's 1 divided by a ridiculously large number. I like to use the example, I have $1 and I'm going to share it with everybody in the world. I am so very generous. Okay, just kidding. But if I take $1 and divide it by the whatever 7 billion people here, we practically get nothing. Now, is it exactly nothing? No, it's not exactly nothing. But this value here is going to get closer and closer to 0. So it'll get closer and closer to 0, but we can never get to it to be a negative value. So I like to write here, nothing to see here. Because this part of the equation, there's no x value that I can plug in to make this a true statement. And if this were standing alone, if this were the entire problem, you could say no solution. But this particular problem, this is all one lovely problem, it has a solution. It's just that this part of it gave it no solution and this part did. Quick little reminder, when I graph y equals 2 to the x, when I graph that, if you think about it, here's my x, here's my y. The value that I really care a lot about is when I get an exponent of 0, because anything to the 0 power is 1. And so my graph is going to do something like, it's going to go through 0, 1. As I plug in 1, 2, 3, this is going to go 2, 4, 8. And then if I plug in -1 and -2, that's 1/2 and that's 1/4. Okay, so this graph is getting closer. It's going to grow exponentially as it gets bigger. So we could say as x goes to infinity, f of x, or y, well, I said y, my bad, y goes to positive infinity. And then on this one, as x goes to negative infinity, as it gets closer, as it gets bigger and bigger and bigger in the negative direction, gets to that, what did I have, negative, some ridiculously large number, y is going to go to 0. So the domain of this function is all real, but its range is from 0 to infinity. It will not include 0. It's going to get closer and closer and closer, but it never gets there. This point, sometimes we call that a pivot point. And that way you can see the transformations. If I were to shift it left, right, up, down, whatever, it's going to, well, we're going to see about what happens to this point, and then we can kind of base everything off of that. All right, good luck. Go practice. I hope this was helpful.